Hey everyone, welcome to this explainer. Today we're going to completely unpack the fascinating, totally hidden physics that make our modern electrical grid possible. I mean, we all interact with electricity literally every single day, right? But behind your walls and inside those massive transformers out on the street, there's this entire invisible plumbing system hard at work. Let's get into how magnetic circuits actually channel flux.
Which really begs the question, how on earth do you control an invisible force? Think about it. How do we take massive amounts of power, move it around, step it up, step it down, and transfer it all without the physical wires even touching? It sounds like absolute magic, but honestly, it all comes down to some really brilliant, structured engineering.
So here's our roadmap for today's explainer. First, we'll dive into the invisible magnetic path, then we'll look at driving the flux, followed by what I like to call the ultimate analogy. After that, we'll cover routing flux, and finally wrap up with transformers in action. All right, let's jump right into Section 1, the invisible magnetic path.
Just like physical copper wires channel electricity right through your home, magnetic circuits use closed loops to channel invisible magnetic forces. And the absolute core component of this path, that's magnetic flux. It's represented by the Greek letter phi and measured in Webers. You can basically think of magnetic flux as the invisible flow being channeled through our circuit. If we use a plumbing analogy, which we're going to be doing a lot today, this flux is essentially the water flowing through the pipes. But, as you know, water doesn't just flow on its own, right? It needs pressure.
Which brings us to Section 2, driving the magnetic flux.
So what actually forces this invisible field to move through our circuit? Well, it turns out it comes down to magnetomotive force, or MMF for short. If flux is our water, MMF is the water pump. It's the active driving force that establishes the magnetic flux in the very first place. And the coolest part? It's wonderfully simple to calculate. You literally just multiply the number of turns in your wire coil, that's N, by the electrical current flowing through it, which is I. This gives us what we call ampere turns. Simply put, the more turns of wire and the more current you have, the harder you're pumping that magnetic flux. But hey, every pump faces some resistance, right? In magnetic circuits, this opposition is called reluctance, represented by the letter S. Just think of reluctance as pipe friction. The physical characteristics of the core material actually determine how hard it pushes back against the flux. So, a longer circuit length is going to increase reluctance, while a larger cross-sectional area and a material with high magnetic permeability, like iron for instance, will dramatically decrease it.
Moving right along to Section 3, the ultimate circuit analogy.
Okay, this brings us to one of the absolute most elegant mathematical relationships in all of engineering. Anyone who is even slightly familiar with basic electricity knows Ohm's law, right? Current equals voltage divided by resistance. Well, check this out. Magnetic circuits follow the exact same logic with Hopkinson's law. Magnetic flux equals the driving magnetomotive force divided by reluctance. So electrical current driven by voltage against resistance is mathematically identical to flux driven by MMF against reluctance. It is quite literally the exact same plumbing, just a different fluid.
Let's look at Section 4, routing series and parallel flux.
Now, because real-world applications aren't usually just simple rings, our invisible plumbing can get a little complicated. When it does, we have to route it either in series or in parallel. In a series magnetic circuit, the flux is perfectly uniform. It's the exact same flow moving through every single part of the loop. But in a parallel circuit, the core actually splits, and the total flux divides among those parallel paths. Conversely, the MMF, our pumping force, adds up across every section in a series circuit, but it stays exactly identical across all parallel branches.
So when engineers are actually out there building these series magnetic circuits, say designing one with a cast iron section, a sheet steel section, and maybe a small air gap, they calculate the total ampere turns needed by just adding up the individual MMF drops of each section. It's simply the magnetic field intensity H times the length of that section L added all together. Piece of cake, really.
And finally, Section 5, Transformers Channeling in Action.
Let's transition from the theoretical physics to some real-world applications, specifically looking at those massive machines that sit on utility poles and power our neighborhoods. Transformers operate on Faraday's law of mutual induction, and they rely entirely on channeling this flux we've been talking about. First, an alternating current voltage is applied to the primary winding. This creates an alternating magnetic flux that's channeled right through the iron core. This moving flux then links to a secondary winding, inducing a brand new electromotive force, or EMF, on the other side. The craziest part? The primary and secondary wires literally never touch. The power is transferred entirely over this invisible bridge of magnetic flux.
Now, transformers generally route this flux in two primary ways. In a core-type transformer, the wire windings surround two vertical legs of the core, which creates a single magnetic path. But in a shell-type transformer, the core actually surrounds the windings, which sit right on a central limb. This shell-type design splits the magnetic flow into two parallel paths on either side. And why do that? Because it actually provides much better magnetic shielding and really cuts down on flux leakage.
Okay, let's face the realities of engineering for a second, because unfortunately our magnetic plumbing is not perfectly frictionless. Channeling alternating magnetic flux actually comes with a cost. We call these core losses, and it's essentially energy that just gets wasted as heat inside the ferromagnetic core.
These core losses basically come in two flavors. First up, hysteresis loss. Because we're using alternating current, the magnetic domains in the metal are constantly flipping back and forth, and they actually lag behind the magnetizing force. This magnetic friction creates heat. Engineers fight this by using specialized silicon steel, which is just a brilliant material science solution. Second, we have eddy currents. The alternating flux induces these tiny circulating electrical currents right inside the solid metal core itself, creating even more wasted heat.
But to stop those eddy currents, engineers do something incredibly clever. Instead of making the transformer core out of one giant, solid block of metal, they slice it into insanely thin laminations. We're talking specifically between 0.35 and 0.5 millimeters thick. Each ultra-thin slice is then coated with a layer of insulation. This effectively cuts off the path for those eddy currents, drastically reducing the heat loss, all while still allowing our magnetic flux to flow completely freely.
Of course, before these massive machines go out into the field, they have to be thoroughly tested. But you obviously can't always just hook them up to a full city grid to see how they perform, right? So, the industry uses two incredibly smart, very safe tests. The open circuit test is performed on the low voltage side, mostly because it's way safer and easier to supply the rated voltage there. And this finds the constant core losses, that iron friction. Then the short circuit test is done on the high voltage side at a very low voltage. This circulates the full load current safely, which allows us to pinpoint the variable copper losses inside the wire windings themselves. And that brings us to just a totally beautiful, elegant rule of electrical engineering. When running these calculations, we actually find that a transformer hits its absolute maximum operational efficiency precisely when its variable copper loss perfectly equals its constant iron loss. It is this amazing, perfect balancing act of physics that ensures absolute minimal energy is wasted as heat while stepping those massive voltages up or down.
We've really seen how these mathematical laws allow us to treat invisible magnetic fields just like water in a pipe. By understanding reluctance, driving MMF, and actively minimizing core losses, human ingenuity has managed to build the silent, static machines that literally keep our modern world illuminated. It really leaves you wondering, though, if we can reliably channel invisible magnetic flux to power entire cities, what other invisible forces in the universe are just waiting to be harnessed? Thanks so much for joining me on this explainer. Keep learning, and I'll see you next time.